This is the 31st lecture of the course MTH 204A for section B. Recall that in the last few lectures, so we were focusing our attention on the main properties of Z, namely these 5 properties, and we aim to these properties in more general settings. So in Z, these properties are consequences of the division algorithm. So therefore all these properties hold in the general setting called Euclidean domain. Then furthermore we have also developed them in the for PIDs. In fact, there we have seen that for PIDs the first one, that is every idealist principle, this is the key thing that implies all 4 other properties. So for PIDs, so earlier our impression was that division algorithm is the main thing behind existence of GCD or irreducible, and the equivalence of irreducibles and primes and unique factorization. Then we went one step further and showed that actually what it suffices is this, that is to have every idealist principle. Now it is very natural to ask whether we can go further, that is whether we can develop these properties in more general domains. So in the last lecture we were dealing with the example of Zx. So the polynomial ring, the ring of polynomials over with integral coefficients. There we have seen that of course Zx is not PID, so this property will not hold. Then the third one also does not hold. These two we have seen, but we have proved that there we have the equivalence of irreducibility and primarity, and of course the unique factorization. So for right now the only thing which is left to us unanswered is the second one. That is, if we are given a pair of elements not both 0 in Zx, whether they always have a GCD or not. Actually we will see here the GCD exists. So how to do that? So let f and g are 2 polynomials belonging to Zx, not both 0. Not both 0, then we use that it can be written uniquely as a product of irreducibles. So therefore how we can do is we can write f as a product like this. So this fi's are irreducibles. Now we will try to arrange the product in a maybe we can say a better way. So among these, so some fi might be an associate to some fj, right? So therefore what we will do is we will club the associate irreducible factors together, and then of course we have to take out the units. So therefore after an appropriate rearrangement we can assume that this can be expressed in the following form: u1 f1 to the power alpha 1 up to fk to the power alpha k, where u is a unit and fi and fj are not associates. Of course each alpha I is a positive integer. Okay. So as I said, the thing is wants to factors as associates, so therefore taking out the unit from them we can put them together, and that is how this takes the form. And then of course we can write g as follows: some g1 to the power n beta 1 up to gn to the power beta n. Okay. So here also we will have the convention that V is a unit, these are positive integers, and these irreducibles are pairwise non-associates. Now there could be another thing that between, so some fi might be associated to some fj, okay. So if that is the case, then we can again further manipulate the second one, and we may assume, we may yeah, so by manipulating it further and arranging and making necessary rearrangements, we can assume that G is of this form. So f1 to the power, let us say beta 1 up to fr to the power beta r, and then the rest of the factors, let me denote them. Okay, so maybe okay, so rest of the factors, let me denote them by some other notation, h1 to the power, so this bit, these are actually to be changed, hl to the power gamma l, okay. And here the first one we will also rearrange, of course, fr to the power alpha r, and the rest of the factors, then we just use a different notation. So let us say EFGA, so here H, and then maybe we can write them by let us say A1 to the power, of course I have to change this, so delta 1 S to the power delta S, okay. So what we are doing is, again let me explain. So we want to, so the prime factor, so the irreducible factors which are common to both of them, of course up to a unit, we by taking out the unit part, we would like to bring the same set of irreducibles, we would like to appear the same set of irreducibles here, I mean in both in the factorization of f and g, and of course those who are which are common, and therefore by relabeling we denote the rest by these notations, by these symbols. So and yeah, so that will result a small change at the level of unit. Now what we do is we consider the following polynomial, so defined as if product of, so product of, so it is from I from 1 up to r, product of minimum alpha I and beta I, okay. So basically, like as I said that we have relabeled the irreducible factors and can assume by relabel, rearrange if necessary, and then we can bring this to in this form. So now let us take this guy, let me call this some D. The claim is this D is the GCD of, D is a GCD of f and g. Why so? That is not so difficult to see, because first of all it is quite clear that this so this is the factorization, I mean this is the unique factorization of D into irreducibles, right. So this is the factorization of D, and we see that the same, so the same irreducibles are appearing both in the factorization of f and g, and the exponents are higher. So therefore there is no doubt that D is dividing f, so easy to see. Easy to see that. So D divides A and B, okay, because if D is given, we know what, we know how what quantity I have to choose to multiply D with so that I get F, and similarly G. And then furthermore, suppose D dash divides A, then we can, so A is therefore this product alpha 1, then alpha r, and then the rest I do not care. So therefore what it means is A being this equals to D times again something which I do not care. Now what we have to do is we have to factorize both d and this part, okay. So factorize d and the whatever is there, maybe I can denote this by k, factorize both d and k, and from the uniqueness of the factorization it is from the uniqueness of the factorization, so the irreducible factors of d, the irreducible factors of d must appear here, right. So the irreducible factors of the right hand side should be same as the irreducible factors of the left hand side, and from that it is quite clear, sorry, I think it will be d dash. So from that it is quite clear, so like this irreducibles must appear here, right. So this irreducibles must appear here, and any irreducible dividing d prime, any irreducible dividing d prime must be these, and therefore from that it is immediately clear that the power, so the exponent of the irreducible f1, let us take f1 dividing this d prime cannot exceed alpha 1. Similarly, when we will consider that for g, that cannot exceed beta 1, hence the power, the exponent of the highest power of f1 dividing f1 in d prime should be less or equal to minimum of these two things, and therefore from this, so similarly for b, I will again explain. So I am saying that you just factorize, so for b you can also have a similar expression, then you factorize d prime and k, and since the irreducible factors on both the sides, they should be same up to associates, which I do not care. So therefore on the right hand side, the highest power of the irreducible f1 that divides d prime cannot exceed alpha 1. Similarly for b we can see that cannot exceed beta 1, so that will be less or equal to minimum of alpha 1 beta 1. So yeah, so therefore from this we see that d prime must divide d, because the first of all the irreducible factors of d prime, the irreducible factors of d prime must be common to the irreducible factors of both a and b. So any irreducible factor of d prime must be equal to some fi, and its exponent has to be minimum of alpha less or equal to minimum of alpha I beta I. That is what we have argued so far. So from this this is immediate, okay. So the if you carefully review this proof again, then you see that the only thing that we have established, that the only thing that we have used to show the existence of GCD is the fifth property only, nothing else we have used, okay. So the fifth property, so not only GCD exists in ZX also, to put it in more appropriate terms, we see that the 5 implies 2 in case of ZX. So let me put it here. So this proof that I have given is nothing I would say new to you. In your school days when we used to find the GCD of, let us say, 2 integers or 2 polynomials, this is the method that we used to adopt, that is we factorize that, and from the common factors we take the minimum exponent. So that used to be the standard procedure, which is also more I mean not only it gives you the existence, also it gives a very concrete, also it gives like it gives you much more, that is its factorization in terms of irreducibles. Okay, so this fact, I mean this not only this exists, also it says that what is going to be the factorization of the GCD from the factors of both the integers. Anyway, so as what I was saying is that in this polynomial ring, this question is answered. We have an affirmative answer for that, but we have seen something more, namely 5 implies 2. So therefore it is very natural to ask that, so again let us see that in case of Zx, so of course the first one we cannot accept, we cannot have, the third one also we lose, and but the rest 3 holds, but however this is a consequence of 5. So it makes us curious to see whether we do have any such dependence between this and that, I mean this 4th one and 5th one, because only 3 properties are hold, I mean they now hold, and one of them is a consequence of another. So it is not so unnatural to ask whether we have any dependencies between them. So let us first investigate that. So recall that how we proved the unique factorization in case of Zx. So this is actually 2 parts. One is the existence, other one is the uniqueness. The existence followed from if you remember the existence of factorization, that followed from that of Qx, because the Qx is a PID. Now in order to show the uniqueness, the only thing that we have required is this 4th property. So therefore given the existence, the uniqueness is a consequence of the 4th property. Actually the converse also holds. In fact we do have this very general observation. Let me put it as a theorem or proposition. So as usual we start with an integral domain and assume that every nonzero nonunit admits a factorization. Here by admits a factorization. By this factorization I mean a factorization. It can be factored into irreducibles. Nonzero nonunit admits a factorization. Okay. So I assume that we have this, then factorization is always unique, that is for whatever nonzero nonunit you pick up, the factorizations are going to be unique. Again let me remind you, unique is in the sense of in the sense of up to a unit, always always unique if and only if and only if all irreducibles are primes. All irreducibles are primes. How to show that? That's actually not difficult to see. So it's actually, as I said, one part I think is already so the part that where, so if all irreducibles are primes, so if part, when all irreducibles are primes, then to show the uniqueness, that is exactly, so the proof of this if part, that is exactly following the following the same strategy that we have adopted earlier. So, similar to the previous, that is the way we prove the uniqueness of factorization in the similar to the earlier. Okay. So, now let us try to prove the only if part. So, therefore, now we are assuming that the factorization, of course, it exists, not only that, it is always unique. So, basically what I am saying is I am now assuming the fifth property for the analog of fifth property for this integral domain R, and I want to show that every reducible is prime. So, let P be an irreducible. We have to show that it is prime. So, therefore, I assume that it divides a pair of elements. Now, therefore, A B is some P times K. Now, what you do is, so given that the factorization exists, so we can factor both A and B into irreducibles, okay. And similarly, so this we can and then we can factor K as well into irreducibles. So, after considering after factoring this A, B and K, since the factorization is unique by yeah. So, since the factorization is unique, that's what we have assumed. So, therefore, P must appear in the factorization of the left hand side, okay, of course up to a unit, and that is exactly, that means either P will appear in the factorization of A or it will appear in the factorization of B. Therefore, that forces P divides either A or B. So, after factoring, A and B, we see that you obtain that. So, this is what we have proved in the generality, that P divides either A or P divides B. So, this is what we see in generality. So, assuming the existence of factorization, it is unique always if and only P reducibles are primes. So, here we see that in ZX the three properties which were the three properties which hold, namely the second one, fourth one and fifth one, these three properties, I mean of course as I said the first one certainly not there, the third one we actually lose, but the rest of course hold, and furthermore all these three are actually the consequence of this property only. So, therefore, this is the main thing, okay, rest are just its consequences. So, this observation naturally makes us hopeful that whenever in an integral domain we have the fifth property, then the other two properties, that is then we must have irreducibles are primes, and of course for any two pair of non-zero elements there should be a GCD. So, this observation from this ZX observation that we have seen for ZX makes us hopeful about that. So, again the main thing is this seems to be the key property which makes irreducibles and primes, and this which makes this to happen, okay. So, that expectation has been grown from this ZX. So, therefore, it is therefore as a very typical practice in mathematics, we must focus on this property that leads us to the more general setup called unique factorization domains, which we have defined towards the end of the last class. As it is already defined, I am not defining it, I will just simply write down UFD. So, what is UFD? First of all, it is an integral domain. So, where every non-zero and non-unit admits a factorization into irreducibles in a unique way. So, here by unique again you have to, whenever we say two factorizations are unique, we also have to keep in mind about the presence of units. Okay. So, this is the definition of an UFD. Before I give examples of unique factorization domains, let me write down the basic properties of UFD, which we have actually almost observed. So, as I said that in case of ZX we see the unique factorization property is the key thing that implies this and that. So, that is that has motivated us to consider this general setup. So, it's like it's reasonable expectation that we should not have any difficulty to obtain this and that in a general UFD, and indeed that is the case. So, I will simply write down the analogues of 2 and 4 holds here, holds for an UFD. Okay. In fact, for the 4 we do have this general theorem. For 2 the strategy, I mean, to show 2 in a UFD, the strategy is exactly similar to the previous one, that is we first we are factorize both the elements, and then we do necessary manipulations and bring the same set of primes which are common, and the same set of irreducibles which are common, and common to both of them, and then take the corresponding each such irreducible, take the least exponent. So, exactly the same thing goes, and that finishes the proof of the second one. Okay. Now, let me give examples of UFDs. So, of course, like every Euclidean domain and in fact not only Euclidean domain, principal ideal domains are also UFDs, because we earlier the unique factorization we earlier obtained for Euclidean domain and more generally for PIDs. Then beyond PID we have seen this ring, we have seen this ring ZX, which is also a UFD. More generally, this is what we have the following. So, this is perhaps the main theorem is if R is an UFD, then so is its polynomial ring over R. Okay. So, to prove this theorem, we won't prove this theorem because like the proof of this theorem goes exactly along the same line of that of ZX. So, let me again recall for you how we proved ZX is an UFD. So, first we observed that every prime integer is a prime element in ZX. That also you can do here. You can show that every prime in R is going to be a prime element in Rx. Then you define primitive polynomials exactly in the same way, that is if the GCD of the coefficients is unit, that is there is no irreducible that divides all the coefficients of the polynomial. Then you prove the analog of Gauss lemma. So, how to prove the analog of Gauss lemma? That is exactly simple, that you consider this quotient, you do this reduction modulo this ideal. So, given any prime element P, given any prime element, I mean so its UFD prime and irreducibles are same. So, given an irreducible P, we consider this so starting with a polynomial, we look at its residue modulo this P, and since this is an integral domain, I mean the product cannot vanish unless one of them vanishes. So, that is how you prove the Gauss lemma in the setup of Rx. Then furthermore you prove that if you have two polynomials in Rx, one of them is primitive, then it can let me write. So, let F be the quotient field of, so field of fractions of R, fractions of R. Okay. So, then you prove that for two such polynomials, if the primitive one divides the other one in Fx, then it has to divide that inside Rx. So, the same argument that we have seen for Zx, and from that you immediately obtain thus in Rx the irreducible. So, from that you will immediately obtain that this both the things, that irreducibles are primes, and then followed by this unique factorization. So, the procedure is simple, although the simple for the same for unique factorization here as well, because we we consider the polynomial over Fx, we consider the polynomial over f of x is a PID. So, you have the factorization, then you clear out the denominator. So, the verbatim repetition of the proof of the fact that this is an UFD, that shows that Rx is also an UFD whenever R is an UFD. Okay. So, I briefly told you how to show this. So, this is basically the verbatim repetition of the proof. Okay. Even the same steps in the same sequence works, the same steps, I mean if you apply them in the same sequence, they will yield the proof. Okay. So, therefore, I leave this to you as an exercise, and then I will further go ahead. Okay. So, here we have given some examples of UFDs. So, this gives a very important class of UFDs. As an immediate corollary, you do have the following. That is, let me first cite a special case, then I will write down the general one. So, let us take any field, let us say for example Q. Okay. So, Qx is a PID. Okay. Now, why do not you consider one step ahead? So, Qx Qy, which is isomorphic to Q of x and y. Okay. So, Qx is a PID. So, hence it is a UFD. So, therefore, this ring is going to be an UFD, right. So, let me again stress that though this ring integral domain in fact is not a PID, because the ideal generated by x and y is not going to be a principal ideal. However, it is going to be a UFD, and then you can proceed further. So, the upshot is, as a corollary to this theorem, R is an UFD implies R x1 up to xn is an UFD. Okay. So, in particular when R is a field, the only one variable polynomial ring has a PID. Beyond that it cannot be PID, but however we do, for any general n, all these are going to be UFDs. Okay. So therefore we now have a large class of examples of unique factorization domains. Now let me get back to this propositions, because this propositions, that is having GCD for any pair of elements, or this having the each irreducible is a prime. These propositions are actually, I mean, more often than not, or maybe you can, if you don't want to say that much, you can say sometimes these propositions actually they turn out to be very useful to show certain integral domains are not UFDs. So let me explain by some examples. So like in general, it's actually difficult to show a given integral domain is a UFD. That's not so easy. But however, sometimes, for example, using this proposition, sometimes it becomes actually easy to show the given integral domain is not a UFD. Okay. So let me now give the examples. So I think I have made my point clear that to show something is an example of a PID, that might be difficult, but however sometimes it becomes relatively easier to show some integral domain is not UFD because of these two things which necessarily hold in a UFD. So let me, for example, let's consider this example. Yeah, so we take this example, z root minus 5. Okay. So here claim is, if you take a equal to 6 and b equal to 2 into 1 plus minus root 5, then these two, I mean these are non-zero and non-units of course, and they are not going to have a GCD. So why so? So in order to show why this is true, we recall that in any general square free integer d, so in z root d we have this norm. So norm of an element a plus root d, I mean a plus db is basically norm of s square minus d b square. Okay. So with the help of this we actually for some specialties we have shown that these are Euclidean domains. I am using the same norm. So what is the point of using this norm? This is very simple. This is actually multiplicative. Okay. So yeah, a plus b root d. All right. So why this is multiplicative? Because this a plus b root d, then you take its conjugate a minus b root d. So they are product and modulus. So that shows that so the conjugate of alpha and then conjugate of beta, you take everything's product and then modulus. That's exactly same as you divide them into two parts. Anyway, so the thing is here the claim is, so I will just briefly tell you the steps. Claim is there is no GCD, they don't have a GCD. I will quickly give you the argument. So if not, that is let D be a GCD. So remember, when we are dealing with general rings, it is not appropriate to say the GCD, because if something is a GCD, then the associate of that is also going to be a GCD, and in a general ring we do not have any natural way to normalize things. So therefore in the general context we do not insist the GCD has to be unique, but however that is not a problem, because after all any two GCDs will be going to be associates anyway. So if this is the case, then immediately it follows that ND must divide, because of this multiplicative property, N6 which is 36, and at the same time this has to be 24. So therefore for ND we have only choices 1, 2, 3, 4, 6 and 12. Furthermore, observe that observe that 6 admits the following factorization, right? Yeah, it admits the following factorization. Therefore, this also, so this 2 divides both, and also 1 plus root minus root 5, that also divides both A and B. Therefore, N2 which is 4, N2 which is 4, that divides NA and NB, and then so this, since 2 and 1 plus root 5 that divides both A and B, if D is a GCD then both should divide D. So therefore N2 should divide ND, and similarly N of 1 plus root 5 that also should divide in my ND. This forces ND, because we have only these choices for ND, ND is 12. So now that's actually, you can show it's impossible if D is alpha plus B root beta into root over minus 5, then that implies alpha square minus 5 beta square is 12, then you can directly show this is not possible. Okay. So thus using the property that any two pair of non-zero non-units, yes, any two pair has a GCD. So if using this in any UFD, we prove that this is not a UFD. So I mean along this same line you can also prove this, which I would leave as an exercise. For any prime P, so let P be an odd prime. Let P be an odd prime, then Z root minus P is not going to be a UFD. So the proof is exactly, it goes along the same line with that of Z root minus 5. There is also another, so here we have proved this is not UFD by using this, by using the analog of property 2. However, we can also show this is not a UFD in a different way, in particular by showing that it can be written as a product of irreducibles in two different ways. So what I mean is, if we do not use this proposition just from the definition, that is whether every element can be factored into irreducibles in a unique way or not, I mean by showing that yeah, there is an element which admits to different factorizations, in that way also, that is from the definition itself, we can show this is not a UFD. Maybe I will just briefly tell you what to do. Like look at this factorization that I have written over there. So for example 6 equals to 2.3, 2 into 3, this is a factorization, and then we do have another factorization. So this is another way of showing the same thing. Now you show that all are irreducibles. Now you show that all are irreducibles. So this is just an exercise. So maybe the norm function, maybe this norm here will be helpful. In fact, that will be helpful. And once it is there, we can then next step you show. So this is just showing from the definition. Next step, show 2 and plus and 1 plus minus are not associates. That is actually easy, because for any unit U, NU has to be 1, that is quite clear. So therefore if two elements are associates, then they must have then they must have a same norm, but here you see the norms are easily seen to be different. Alright, so from the definition itself you can also show z root minus 5 is not a UFD. I would like to leave also these verifications to you as exercises, that when d is minus 6 and minus 10. So like these also you can do by this similar argument, that is exhibiting something which has two different factorizations. So when d is this, then z root d is not a UFD. Okay. Let me give you another non-example. So like so far in the non-examples that we have shown, either we have used the analogues of 2 or we directly proved from the definition. Now I will give you I will talk about an instance where we can show the given integral domain is not a UFD by showing that there we have irreducibles which are not primes. So the example there is also quite simple. Just take z root 5. So here our approach would be the very simple thing, that consider the 4. So these are standard examples, 1 plus root 5 into 1 minus root 5, okay, and that can also be written as 2 times 2. Then you just have to show. So this is somewhat some manipulation you have to do, some cumbersome manipulation you have to do. This is not just immediate, like you need to do some calculation, but however those are kind of quite routine computations. So then show that. So that two things. One is of course 2 is an irreducible. So if to do that you have to do some calculation, and 2 does not divide 1 plus minus root 5. Okay. So therefore we do have an irreducible which is not a prime, therefore this obstructs z root 5 from being a unique factorization domain. Okay. So enough with examples and non-examples, especially we see that how its properties can sometimes help us to show certain domains are not UFDs. Now we should move to something else. So now let's come to the main point, that the main theorem, that if R is an UFD, so then Rx is also an UFD. So therefore if we take a polynomial, okay, let me just write. So then, as I said, the main theorem is R is an UFD, Rx is an UFD, so since this is an UFD, so therefore if we take a polynomial in Rx which is nonzero and non-unit, we would like to have an efficient method to factorize that into irreducibles, okay, because it's an UFD, so factorization exists. So since it's factorization guaranteed, we would like to have an efficient method for factorizing any nonzero non-unit polynomial. And of course in order to have that factorization, what we must have beforehand is an efficient way to determine when a given polynomial is irreducible, because if you can't determine that, then this factorization I am talking about cannot be dealt with, right? Because if we can't check the factors are irreducible, then we cannot say that our factorization is the factorization of fx into irreducibles. Okay. So from now onwards, maybe for the rest of this lecture and the next and in the possible next lecture, we will deal with factorizations. So an concrete case of the following is when R is Z. So that is, we would like to factor polynomials with integral coefficients. So now let us come to the problem of factoring. So let us try to find the given a polynomial, let us try to find the linear factors of those polynomial, because those linear factors, they can be easily seen to be when they are reducible or irreducible. So for linear factors, easy to see when they are reducible or irreducible. So maybe first I should do it as a proposition. So we now bother about linear factors. So suppose fx is this, is in Rx, where R is of course assumed to be an UFD. Let us take the degree is n. Then we have the following. So suppose a linear polynomial, I mean assume that B1 is non-zero. A linear polynomial in Rx, this divides fx. So this linear polynomial is a factor of fx if B1 divides an and B0 divides A0. So the proof of that is very easy. If this is what we have, so something will be there, let us say some alpha x to the power n minus 1, I do not care what alpha is, and the middle things I also do not care, then let us say some beta. So from this is clear that B1 times alpha is an and B0 times beta is A0. So this is immediate. So what this says is, if a linear polynomial is a factor of fx, then we must have these conditions, and furthermore, yeah, so when this division is means division in Rx, and furthermore this divides fx. So suppose we are having a linear, suppose this linear polynomial, okay, I should put in complete terms. Let B1 B0 in Rx, assume this is a linear polynomial, B is primitive, assume that is primitive. So a primitive linear polynomial divides fx if and only if, so minus B0 by B1 is a root of f. So here we view f. So let me denote the field of fractions by, okay. So earlier we have seen if a linear polynomial divides, then what will happen. Now for this is furthermore, if the linear polynomial is primitive, then that is we do not have the GCD is a unit, then we do have a necessary and sufficient condition. So we view f as a polynomial over this field of fractions, and if this is a root of the polynomial in that field, so that is exactly a necessary and sufficient condition for a primitive polynomial to divide that. And the proof of this is also a routine one, like so this is just the usual division algorithm. So B1x plus beta naught, this divides f in this divides f in Rx, so therefore that will divide also in Fx. So therefore in Fx we have something like this, Qx times we can take B1 outside, x plus B naught by B1. Okay. So this is the factorization inside Fx, and that shows this is a root. And this if and only if. Okay. And the third one is third one says that, maybe I should write down the third one here. So given f is monic, if f is monic and given f is monic and R is in f is a root of, so I will explain root of f, then R will be in R. So they again it's very easy to see the consequence of the previous ones. Write R as a fraction where the numerator and denominator do not have anything in common. So therefore you can so since they don't have any irreducible factor in common, so we are in a situation of we apply 2 and then we apply 1 to that shows the denominator will divide the leading coefficient of f, which is a unit, I mean which is 1, so therefore we are done. Yeah, so thus the linear factors, given a polynomial, the linear factors can be easily found, because first of all this says that they have to come from the divisors of a1, I mean an and a naught. Then furthermore if we take such a polynomial, if we take such two factors and construct the polynomial by clearing out the common GCD, then determining that whether it is going to be a factor, that is easy because it is equivalent to see whether the corresponding fraction is a root of f. So thus this shows the linear factors can be found easily. Therefore now we should go for finding factors of higher degree. So as I said, for linear polynomials it's for linear polynomials it is very easy to see when they are irreducible, namely any linear polynomial which is primitive has to be irreducible, but for higher degree polynomials this is not the case, because what we have is the primitive polynomials, non-constant primitive polynomials which are irreducible in the field of over the field of fractions, they are going to be reducible in Rx. So the scenario is not so simple. Therefore we first need to develop some ways to determine when a given polynomial is going to be reducible. So that is exactly done using this method of reduction to reduction modulo prime equivalent irreducible elements. Let me first talk about this lemma. So again what I am going to do is I am going to talk about some results which will show that under certain circumstances, of course the cases which we will be dealing with, in those cases these are going to be very helpful. So this results say under certain circumstances the polynomial, the given polynomial can be shown to be reducible. All right. So let me first do. So this is a quite general one. Let R be a commutative ring. Let R be a commutative ring and I be a proper ideal. I be a proper ideal. Let F be non-constant and monic, Okay. If so, we can look at the residue of f modulo I. So So, we reduce the coefficients of f modulo I. If this turns out to be reducible, then f is irreducible. Okay. So, this is and we do have another variant of this lemma as well, which sometimes becomes more useful and is less stringent than this, because here the polynomial which we are considering, they have to be monic. They have to be monic, but the next lemma that we are going to talk about, maybe I should say lemma 1 and lemma 2. This does not insist that the leading coefficient has to be a unit. Rather, what this says is the following, that but here of course this is for an UFD. So, let this R is an be an UFD, and Fx is this. Let P be a prime, P in R be a prime, such that we have two things: P does not divide an, and F bar. So, similar kind of statement is here, is irreducible. Okay. So, suppose we have a prime P such that which does not divide the leading coefficient, and after reducing the polynomial modulo P, whatever we have is irreducible, then f will be reducible. But however, you have to be slightly careful, f is irreducible in over fx. Okay. And furthermore, so f is irreducible in fx. If furthermore we assume that f is primitive, then f will be reducible in qx. So, moreover, if f is primitive, then it is irreducible in qx as well, in rx as well. Okay. So, try to compare these two statements. I will of course prove the proof of these two statements actually go along the same line. So, this is for engineering commutative ring, a proper ideal, but here we insist that the polynomial has to be monic. Then after reduction, if it is irreducible, then the original has to be reducible, and this is slightly, this is for the restrictive setup of UFD, but however here we do not insist that the coefficient has to be monic, coefficient has to be unit. However, if we can find a prime which does not divide an, and after reduction the polynomial becomes irreducible, then the given polynomial must be reducible in fx, and so this is actually necessary because of this very simple counter example, that if you take fx to be let us say 3 plus 3x, so fx to be 3 plus 3x over zx. Okay. So, then take p equal to 2, you see, then after reduction you will have 1 plus x, which is of course irreducible, but this is not irreducible in zx. So, here like immediately we cannot jump into the conclusion that this f is going to be reducible in zx, because there could be a irreducible common factor of the coefficients, but once it is not there, namely when f is f is primitive, then we can simply say this is irreducible in Rx. So, thus combining these two, if we start with a primitive polynomial and find a prime p which does not divide the leading coefficient, and after reducing the residue becomes irreducible, then we can safely say the polynomial that we have started with has to be reducible. Okay. So the proof of these two statements actually go along the same line. Maybe I proof. I mean, proofs are very easy. So first let me show you the utility of, let's say, this second lemma, and if after that time permits, then I can give the proof, or I can leave the proof as exercises, or maybe I may give the proof in the next lecture. But however, first let me explain the utility. So what is the point, what is the what is the benefit of the reduction modulo any prime? The reason is simple, that let me explain by an example. So if I take r equal to z, so there, and take p be any prime, so therefore we are reduced to this finite field consists of exactly p elements, and so in this finite field, it's given any degree, we do have only finitely many polynomials of that degree, right? We do have finitely many polynomials of that degree. So therefore, since we have only finitely many polynomials, we can find which one of them are irreducibles. In fact, that's exactly an efficient method of doing this, is the method of sieves of Eratosthenes. So I will explain by an example. Let's say p equal to 2. So the way we do that is corresponding to each degree, I will write down all the polynomials, then find, starting with the linear polynomials, then I will find out which one of them are irreducible, and then from the polynomials of higher degree, I will simply cross out those which are the multiples of them, and then we will continue like that. So maybe I should say that. So degree 1, we do have only two polynomials, x and x plus 1. Okay, so of course they are irreducible, easy to see. Then degree 2, we have how many polynomials? X squared is there, x squared plus 1 is there, x squared plus x is there, and x squared plus x plus 1, this is there. So you see that for the first three, they are either divisible by x or x plus 1, so they are irreducible. So they are reducible. So therefore this is the only one which is left irreducible. Okay. So thus for degree 2 factors, we have see there is on exactly one polynomial of degree 2 which is irreducible, and then by using this information I will show how to show a polynomial which is irreducible. So consider this x to the power 5 plus x cube plus 1 is a polynomial in z modulo 2zx. Okay. So if this is reducible, then if this is reducible, then one of these factors, just a minute, one of these factors must have degree 2, right? One of the, so if it is reducible, then one of these factors must have degree 2, and you see that easily these linear factors, they don't they do not divide this just by direct computation. So this forces, if this is reducible, just a minute, then so we do have exactly one irreducible factor of degree 2. This must divide the given one, but this is not possible because remainder is you can easily see that remainder is non-zero. Okay. So therefore this shows this is irreducible, and as a consequence if you take this polynomial over z, so this is a polynomial over zx, polynomial in zx, so monic polynomial. by reducing in modulo 2, we will get this which is shown to be reducible. So, by means of this lemma 2, this becomes irreducible. Okay. So, this by an example I have illustrated how this lemma becomes useful, becomes quite useful sometimes. The main reason is, as I said, that in this finite field, I mean main reason is sometimes in this because of the nature of this field we have only finitely many polynomials corresponding to a given degree. Okay. So, I think this lecture will finish here. The next lecture either I may give the proof of these two lemmas or I can leave them as exercises. Anyway, so that I will finish here.